please tell me that is it difficult for you to connect to Zoom or not?
No.
No?
No,
No.
I think the connection is pretty bad.
Very bad?
My connection is unstable, so sometimes it's got lagging. So.
It's like all the time.
I don't know why, because today I use internet connection from my home, not from the USDH. Anyway, if you have some problems in connection, please let me know. Okay, because I begin right now because the class today is very long, so I will begin right now. And as always, before any class, I always make a short review of what we studied last week. And last week we studied the system of linear equation, and it is here. A system of m linear equation in n variable is something like that in the screen you see. And we have coefficients, we have a variable or unknown xi, aij is a coefficients. If ai1 is non-zero, we call it a pivot or the leading coefficient. And in that case, the unknown or the variable x1 will be called the leading variable or leading unknown. And a system of linear equation will be consistent if it has at least one solution, and it has no solution, we call it inconsistent. But more than that, every system of linear equation can have one of three possibilities as follows. It can have exactly one solution. It can have no solution. But more than that, it can have infinitely many solutions. So we have three possibilities. And as we know in high school and here also, usually given a system of linear equation, you are required to solve it, means we need to find on the system, on the solution. And here we call it a solution set. In order to do that, usually in the high school, we try to transform it into a new system of linear equation, which is easier to find solution. But the new one, the new system of linear equation must be equivalent to the first one, means it has the same solution set. And in order to do that, in high school or here also, we use what we call the elimination or phương pháp khử. In order eliminate operation, it can eliminate equation by using one of the following operation. We call it elementary operation on the system of linear equation. We can interchange two equations. We can multiply an equation by non-zero constant, and we can multiply an equation to any number, and then we add to another equation. And if we apply those operations on any equation in the system, we get a new system which is equivalent to the first one. So we apply those operations to change our system into a new system which is easier for us to solve it. And we can summarize it. So please, your student, please switch off your microphone. Please switch off your microphone. You switch it on only when you have something to ask me. So here we try to give it in a systematic way by give it the name Gaussian elimination or Gauss-Jordan elimination. And in order to do that, we need to define a matrix. And here on the screen, you see a matrix is a rectangular like that. It consists of m rows and n columns, and each element inside the table has named the entry. And a matrix with m rows and n columns will be called of sign n by n. And now with that, a system of m equation like that now can be written in only one single equation, but that is a matrix form equation. Is here. And A to be that, the matrix, the coefficient matrix, X to be the columns of unknown of variable, and B is a column of the right hand side. And first we accept to write it down. And today we know what is it, what does it mean, that equation. And the name A is a coefficient matrix. If on the right hand side of A we add one more column, that is a right hand side column, we get a new one, we call it the augmented matrices. And similar to equation, for system of linear equation, we can do some elementary operation on system, and here we can do what we call elementary row operation, and it is absolutely similar to what we do in the elimination. We can interchange two rows. We can multiply on entry on a row by a non-zero number, and we can add multiply of a row to another row, and on those operations are denoted by that. I require you to remember the notation like here. And the row equivalent means in solving a system of linear equation, we have the notion of equivalent system of linear equation, means two systems has the same solution, and this system can be obtained from the other by applying some operation. And here again, two matrices are said to be row equivalent if one matrix can be obtained from the other matrix by applying a finite number of elementary row operation described above. So that is a notion. And here is some example show you how we can use the matrix to write down the procedure to solve a system of linear equation by using elimination. And it is here, I will not repeat it here, you can read it in the slide I up on the Moodle a long time ago. And it's here, and finally you get that thing. And whenever you apply those operations, you make the augmented matrix to be like that. It's very easy for you to write down the solution here, to find the solution. And that form of the matrix is very special. It has named row echelon form. The row echelon form and the reduced row echelon form is defined in this slide. I'll show you here. And by example, it's very easier for you to remember what is a row echelon form, what is reduced row echelon form. And pay attention that the last two examples show you those are not row echelon form and also not reduced row echelon form. Then with that notion of matrix, we call the procedure for reduce a matrix to a row echelon form has named Gaussian elimination. And the procedure to reduce a matrix to a reduced row echelon form, that is just a little more than the above elimination, which has named Gauss-Jordan elimination. That is, now we have two notions of elimination, and we apply one of those things to solve a system of linear equation. And we have the notion of homogeneous system of linear equation. A system of linear equation will be said homogeneous if on the right hand side are zero. It's very easy to imagine. And obviously, it always has trivial solution. That is a solution consisting of on zero. If you look back here, if we substitute x1 equals 0, x2 equals 0, x3 equals 0, and up to xn equals 0, on equation now becomes equality. That is the reason why we have always have trivial solution. And obviously, we need to find if a homogeneous system of linear equation has a non-trivial solution or not. Then, because it always has a trivial solution, we say every homogeneous system of linear equation is consistent. And in case the homogeneous system has fewer equations than variable, it must have infinitely number solution. That is what we studied last week. And today we continue with the lecture number 2. The lecture number 2 will deal with operation on matrix. So we go here. First, recon here. A matrix A is a m by n matrix is something like that. That is a rectangular table consisting of number as entry. We can denote it like that by anyone. Any of these notation are acceptable. And the ij's entry is denoted by aij, with the index ij. The number of rows are m, the number of columns is n, the size is m by n. Given such a matrix, it can be divided into rows and columns, and the ith row will be written like that: I to be I1, I2 up to AIN, and we call it the row matrix, and it is the ith row. And similarly, it can be divided into columns, and j's column denoted by cj, consisting of A1j, A2j up to AMJ, those entries standing on the same column, the column j, and it is a columns matrix. And in the case the number of rows equals the number of columns, we call it square matrix. Square matrix. And here is an example. It's a small one. A 3 by 4 matrix A like that is divided into 3 rows, R1, R2, R3. And it is divided into columns like that. C1, C2, C3, and C4, and here is a C3. Also, any matrix can be divided into small block like that by using horizontal and vertical line, dash line like that. In that case, each block does not necessarily be row or columns like that. It can be bigger, like here. A11 is a 2, 3 matrices. We call it a sub matrix like that. That is a way to partition or to decompose a matrix into sub-matrices. And we have the notion of diagonal matrix. So then diagonal matrix is something like that. A, we denote it by DIAG of that. It is a square matrix with any entry as 0 except those lying on the main diagonal. And on the main diagonal is D1, D2, Dn is putting here. And we have one more thing, that is a notion of trace. For a square matrix A like that, the trace of A equal A11 plus A22 plus ANN. That is something about the matrix. And here is an example. For A to be that, we have two rows. The first one is R1 here, R2 is here, and three columns, C1, C2, C3 is here. Next, we define two matrices are equal to each other. Two matrices A and B are considered to be equal to each other if they are of the same sign, m by n. But more than that, we require that the corresponding entry are equal to each other. Means we have Aij equal Bij for any I between 1 and m, and for any j between 1 and n. So that is the notion of two matrices which are equal to each other. With that, here is some examples. It's very easy. If A, B like that, and it is said that A equal B, then A must be 1B equal to C equal 3 and D equal 4. Easy. Now we define the addition of two matrices. Suppose that A and B are matrices of the same sign m by n. Then the sum A plus B is a new matrix of the same sign m by n. And the entry is obtained by we add corresponding entry of A and B. And you can look at the formula on the screen. It's very easy to imagine. Here is an example of matrix addition. Suppose that we have A to be Z1 and B to be Z1. You add them together. So we add the corresponding entry is here. And the reason is here. Another example is here. We have two columns matrix and we add them together. We get that is the columns consisting of on 0. The next example, that the previous operation is very easy. Very easy. Now the next operation has named scalar multiplication. Scalar, why scalar? Because here we have a number C. C is a scalar. Suppose that A equals a matrix of any sign m by n. Then scalar multiplication CA is a new matrix of the same sign, like here. The entry is obtained from entry of A by multiplied by the number C. And with that, we can define the matrix subtraction. In Vietnamese is a phép trừ của ma trận. If we want to define A minus B, first we take B and we multiply by the number minus 1. And then we add them together. That operation is scalar multiplication we have just defined. And the addition of two matrices of the same sign we defined already in the previous slide. So we get the notion here. Now the next example show you anything we have just studied here. Given A to be that, B to be that, The first one, you need to find scalar multiplication of C and A. Second, you need to find what is a minus B, means minus 1 multiplied by B. And the last one, you need to find CA minus B. It is very easy example here. CA to be that, and by definition, you multiply C by any entry here, and you get that one. Minus B equals minus 1 multiplied by the matrix, and again, you get that one. And the last one, CA minus B, means we have CB here. We have that minus that one. And what you get is here. So you see, it is very easy for those operations of matrices. The most difficult, and it is very easy for students to make mistake, that is what we call a matrix multiplication. So please pay attention to any details on this screen. Suppose that A is M by N matrix, B is N by P matrix. Then we define the product or the multiplication of A and B to be a new matrix denoted by C of the sign M by P. And Cij, each entry Cij is given by the very complicated formula like that one. So first, I call your attention to the sign of A and B. In order to define the product A and B, we need to have the number of columns of A equals the number of rows of B. Without that, we cannot multiply A and B. That is the first requirement we need to have. Then we pay attention to some more things here. The number of rows of A and the number of columns of B. That is the sign of the product. So C has a sign M by P, where M is the number of rows of A and P is the number of columns of B. But that is still easy to imagine. But what is Cij? If you look at the complicated formula like that, it's very difficult to remember. But however, if you draw it down in the picture, not like in a formula, not like in mathematics formula, it is easier for you to remember. Now, Cij, that is what you need to find here. In order to find Cij, so first I take the ith row of A, and then I take the jth column of B. And because our requirement for the number of column of A and the number of column of rows of B, we have that rows contain exactly n entry, and the same with the jth column of B, it contains n entry. So now we take the product of the first entry here and the first entry here, so we get that term. We continue. We take the second entry here and we multiply by the second entry here. We get the second. Terms here, and so on. And finally, we get the last entry here and multiply by the last entry here. We get that thing. That is the way we compute Cij. In order to remember that, you need to remember the picture here. Then before going further, I would like to tell you, for the addition of matrices, you can verify that A plus B equals B plus A. But for the matrix multiplication here, in general, we don't have that means in general A, B is different from B, A. We are going to see it later. Now we begin with the example. Here we are given a 3 by 2 matrix A and 2 by 2 matrix B. Then the number of column of A is 2 and the number of rows of B is 2. So it satisfies the requirement. Means we can multiply A by B. Then A by B to be like that. But I want you to look in the detail. That one, the first one, the first entry here. How we get it? We get the first column here and the first row here and the first column here. We multiply corresponding entry. We get that one. We continue by take the second row here and second column here. You get that one. And so on. We try it and finally you get that one. So from the very beginning, it somehow not so easy for you to remember. But if you do some exercise, some examples on the textbook or by yourself, write it down on the paper, you will see it is not so difficult to remember. Now I coming back to the matrix form of a system of linear equation. Given a system of linear equation, it is written like that. So it consists of m linear equation in n variable in n unknowns x1, x2, xn. But we try to write it in the matrix form. It will be something like that, like down here. So you see, now we have only one equation, and that is the multiplication of two matrices. A is a coefficient matrix, X is a columns of variable, and if we multiply two matrices to each other, you will get the left-hand side of the system of linear equation. If you multiply that row with that column, you get the first, the left-hand side of the first equation. If we multiply the second row with the column of variable, you will get the left-hand side of the second equation, and so on. And the last row here multiply with the column of variable, you get the left-hand side of the last equation. And here is the columns of right-hand side. And those system of linear equation now becomes only one single matrix equation. Only one single equation, but that is equation between matrices like that. That is why we say matrix is very useful in writing the solving procedure of a system of linear equation. Now we are going to study property of matrix operation. So far we define only three basic matrix operation. We are going to define two more things. One is very easy and one is difficult in some way. Anyway, we fix that. So far we have three basic matrix operation. The first one is a matrix addition. The second one is a scalar multiplication. The third one is a matrix multiplication. So we have two multiplication and only one addition. Now before telling you about the property of operation, I tell you the definition of two things, two new things, two special matrix. The first one is zero matrix. The zero matrix denoted by 0 m by n. That is an m by n matrix consisting of on zero, on entry zero, like on the screen here you see. The next one is identity matrix of order n. That is a square matrix. Square, you know already, that is any entry except the diagonal 0. And identity matrix requires that on the entity lying on the main diagonal at 1. So it is here. They are very special here. Now, property of matrix addition and scalar multiplication will be described here. I will not prove it. I will show you, and you can apply it in doing your exercise. And most of those properties are very similar to that of number, of operation on number. So it is very easy for you to follow. The first one, the A plus B equal B plus A. I require you to verify it by yourself. A plus B plus C equal A plus B plus C. Means if we add B and C first and then we add to A equals, if we add AB first and then add to C, that has named the property of associativity. And the first one is a property of commutativity. Now is something else. Suppose that we multiply C and D first, that is the product of two numbers. And then we take scalar multiplication of that number with A. It is equal that if we multiply D by A first and then multiply by C. And if we multiply A by the number 1, nothing change. We get 1. You get A. Okay. If we take C multiplied by A plus B, you get that CA plus CB. If you get C plus D multiplied by A, you get CA plus DA. That is some property for matrix addition and scalar multiplication. Now property for zero matrices. First, if A is any matrix of any size m by n, then if you take A plus zero matrix, nothing change. You get A again. Of course, we need to have 0 and A of the same size m by n. And if you take A plus minus A, you get 0 matrix. If we take C, any number C multiplied by A, we get 0. Then we can have only one possibility. C is 0 number, or A must be 0 matrix m by n. You can have only one of that possibility. And those property give some name. The first property saying that 0 m by n is additive identity for the set of on m by n matrices. I will not tell you, but I give you some meaning. The additive identity means it is identity for the addition operation we define. And here's minus A is additive inverse of A, means it is an of A according to the addition. And what is the inverse of operation and identity of an operation? I suppose that maybe some of you will know later, not right now. Next, I explain to you some property of identity matrices. It is here. Suppose that A is m by a square matrix of order n, and In denote the identity matrix of order n, means A and I are of the same sign. Then if we multiply A by In or In by A, we get the same thing, that is A. Means if we multiply by A by identity matrix on both sides, nothing changed. We obtain again the matrix A. And here are some properties for matrix multiplication. The first one is here if we multiply B and C first and then multiply by A, it equals A multiplied by B and then multiplied by C. That is a property of associativity. And the second property saying A multiplied by B plus C equal A multiplied by B plus A multiplied by C. That has named property of distributivity. And here is a distributivity from the right. And next one, like that, is again distributivity, but now from the left. And the property number 4 saying C multiplied by the product of AB when B equals that, we can put C in the first factor or the second factor as the same. But however, the property number 5 saying that in general A, B is different from B, A. That is a property of non-commutativity. That will be explained later. Now I introduce two new just only one operation, that is transpose of a matrix. Suppose that we are given A matrix of sign m by n, like here. Then we denote A T to be that matrix, that is a matrix of sign n by n. Please pay attention to the sign here. And you see, it's very easy to define that. We call it AT, the transpose of A. T stands for transpose. And how we can get AT? We do as follows. We take the first row of A and we transform it into the first column here. We continue by taking the second row and we change it into the second column here, and so on. And finally, the last rows will be changed into the last column here. So that is a transpose of a matrix. And obviously, if we do it again, then you get back the A. Now here's the example, very easy. A to be like that, then AT to be like that. The column matrix, then transpose will be row matrix, and A to be that, then AT to be that one. And if A to be that, then AT, A transpose to be that one. Very easy and nothing to check here. And some property for transpose. As I told you, if we take transpose and then we take transpose once again, you will see once again now column will going back to rows, column going back to rows, and because of that we get back to the original matrix A. And if we take transpose of a sum A plus B, it equals A transpose plus B transpose. And if we take transpose of a scalar multiplication, you get A transpose multiplied by the same number C. But the last one, A B transpose equals B transpose multiplied by A transpose. And your homework, please verify that at home. Please do it. It's very easy to verify that one. But that exercise will give you a chance to revise what is a matrix multiplication and what is a transpose of a matrix. Is very easy. But however, it's very useful for you to remember the formula. And once we mention about the transpose, we say I will introduce the notion of symmetric matrix. A square matrix A will become symmetric if A equal AT. So, because symmetric is the name is what is very geometric. So I want to tell you, symmetric in Vietnamese is đối xứng. So what does it mean symmetric for a matrix here? It means it is symmetric about the main diagonal. Means if A to be like that and is symmetric, then that one must be that one, that one must be that one, that one must be that one. Means A must be 2, B must be 3, and C must be 5. That is the meaning of symmetry. Or if you look at the definition here, you will see A to be that, so AT to be that one. So because the requirement A equal AT means A now equal to B equal 3 and C equal 5. That is exactly what I explained to you here by the meaning of symmetry. Another homework for you. That is, given A is a matrix of any sign. The first one, you should verify that we can always multiply A and AT and AT and A with that order. Always. You remember that the requirement for define the product A and B, that is the number of column of A must be equal the number of rows of B. And here, in both cases, it is satisfied naturally. And then the second homework, that is, please verify that both product A, AT, and ATA are symmetric. Matrix. So please verify it. Now, next I explain to you, in general, the product A, B, and the product B, A are different from each other. Let's consider A is an M by N matrix and B is an N by P matrix. For A, B like that, we can have only C situation as follows. The first one, if M and P are different, then we cannot define the product, we cannot multiply B, A, because in that case, the number of column of the first matrix does not equal the number of column, the number of rows of second. The number of column of the first is P, the number of rows of second is M, and P is not equal P. So BA is undefined. We can define AB, but BA cannot define, so we cannot have AB equal BA. So that is the first situation. The second situation, that is in case M equal P, means in that case we can define BA. M equal P, but if M is different from N, then the product AB is a square matrix of order N. But BA is a square matrix of order n. And because m and n are different from each other, means A, B, and BA are matrices of different sign. So they cannot be equal each other. And the last situation, that is when m equal p equal n. Then in that case, we can define A, B, and also BA. Both product can be defined. And both product are of the same sign m by n. But even in that case, the product can be different, as we are going to see now. We take A and B like that. They are square matrices of the same size 2 by 2. We multiply them together. A, B, we get that one. And B, A, we get that one. And obviously, the reason are different. Means we have A, B is different from B, A. So our conclusion is that in general, A, B, and B, A are different from each other. The last, before the break, that is the notion about the cancellation. The cancellation law means in Vietnamese we say luật rút gọn. So what is it? What is it? Luật rút gọn. What is the cancellation law? In doing with number, whenever you have the product of two number AC equals BC, if C is non-zero, is not zero, then you can divide both sides by C, you get A equal B. That is what we call cancellation law. But for matrix now, suppose that we have A, the product of AC equal BC, and C is not zero matrix, and in general, we cannot imply A equal B. In that case, we say cancellation law is not valid. We can have it only in the case if C is invertible, then we can imply that A equal B. And in case C is not invertible, then A, in general, A is different from B. And that is what we say cancellation law is not valid. So what is invertible? That is what we need to define it today. Not right now, but today. But before that, we see the example. Suppose that we are given three matrices A, B, C like that of the same size 2 by 2. We multiply them together. A, C equals that. B, C to be that. And obviously, C is not zero matrix, but even though from AC equal BC, we cannot withdraw, we cannot imply that A equal B, because in that case, A and B are different from each other. Means here, cancellation law is impossible. So now we take a short break, and then coming back, we study what is the inverse of a matrix. So we stop, we take a short break of 5 minutes, please.
Okay, teacher.
So let's coming back to the class. Have you all of you are in? Please answer me.
Yes.
Yes.
Em thưa thầy cho em xin phép một chút ạ. Bạn Đỗ Hữu đang có nhờ em xin phép thầy là cho bạn ý nghỉ buổi học
Mình
hôm
đọc
nay.
thấy rồi. Ok, không có chuyện gì em.
Dạ vâng ạ, em cảm ơn ạ.
Anyway, we continue. Just before the break, I tell you one thing, that is invertible matrix, but without definition. So now we are going to define it. The inverse of a matrix. Now we consider a square matrix A m of the order, A of the order n. If we can find a matrix, a square matrix B of the same sign n, so that A B equals B A equals identity n, then we say A is invertible or non-singular, and in that case we say B is the inverse of the A. So now we know what is a matrix is invertible. Then I give you some more names. A matrix A, which we cannot find a matrix B satisfying those things, we say that A, in that case, A is a singular matrix or A is a non-invertible matrix. And in case A is invertible, we can find only one inverse, only one matrix B satisfying that. So because we have only one inverse, then we denote it by A to the power -1 like that. Then those formula will becomes A multiplied by A to the power -1 equals A to the power -1. A equal identity. We write it here, but anyway, we call it A inverse, right? Like that. I here is I means identity. I here and I here are the same. So that is identity matrix of the order n. Then one of your duty will be find the inverse of a matrix. And here I am going to explain to you how we can do it. I begin with an example that is a small one, very easy to see. Suppose that we are given a square matrix A of size 3 by 3. Then we need to find inverse, mean we need to find a matrix X like that with on 9 and 3 here, satisfying that. If we multiply them together, we get the identity. If we multiply two matrices on the left hand side, we get that one. Oh, sorry. First, I denoted the first column by C1, the second column by C2, and here the third column by C3. We do the same things for the identity. We get B1, B2, B3. Now, if we multiply the left-hand side, we get the following. If we multiply A, I mean A here, we multiply them by the first column C1, you get the B1. If we take A multiplied by second column here, you get the second column here. That is the second system of linear equation. And the last one, if we take the A multiplied by the last column, we get the last column here. So here we have 3 systems of linear equation in the matrix format. We can write it in that way. A multiplied by C1 equal B1, A C2 by B2, A multiplied by C3 equal B3. Of course, we know that in order to solve a system of linear equation, we can apply Gauss-Jordan elimination. So we need to solve 3 systems here. But our observation is that all 3 systems has the same coefficient matrix. So if we apply Gauss-Jordan elimination methods, we can apply it at the same time for three systems of linear equation to find the solution. And here is what we are going to say. If we need to find the inverse of a square matrix A, we do as follows. On the right hand side of A, we write the identity matrix of the same size. Means if A is a square matrix of order n, then now that together we get a matrix of size n by 2n. Now we do as follows. We apply Gauss-Jordan elimination to transform that part into the identity. Then the same procedure will change, will transform that part into something that will be A minus 1. And I repeat that here A means identity matrix. I explain it by the example below, and you see we do it step by step. Suppose that we are given A, very small one, A to be 2 by 2 matrix like that. We need to find the inverse of A, means we need to find a matrix X like that, so that A multiplied by X, we get the identity here. And X consisting of four entries, X11, X12, X21, X22, like that. Now, if we multiply them together on the left hand side, we get that one. And from that, you get two systems of linear equation. The first one is here. The second one is here. So we have two systems of linear equation. And again, look back. The coefficient matrices are the same. 1, 4, minus 1, minus 3. So in order to solve the first system of linear equation, we write down the augmented matrix here. And we apply those operations. We get that one. That one is already reduced echelon form. That is, from here to there, we apply already on the Gauss-Jordan elimination. Then from here, we get the solution. The X11 is minus 3, X21 is 1. Now we apply the same procedure to solve the second system of linear equation here. We write down the augmented matrix of the second one. That is the same A, the coefficient matrix is here. The difference only in the last columns. The last column is the column here. Then we apply the same thing, same operation here. You get also here, that is reduced row echelon form. And from here you get the solution that like that one. So here in this line we apply Gauss-Jordan elimination to solve the first system, and in that line we apply the same Gauss-Jordan elimination to solve the second system of linear equation. And with that we get the X equal inverse to be that one from the solution we find here. But however, because here we apply the same operation in the Gauss-Jordan elimination procedure, we can do it not in two lines like that, only in one line, and we do as follows. The coefficient matrix A is here. Now we write down the identity, and we apply exactly the Gauss-Jordan elimination as in the previous here. If we look at here, and here we apply the same things, and the first part now becomes the identity, and the second part now becomes that one. That one is exactly A minus 1, A inverse. You can see it's A inverse. So that is something explained for you how we can find the inverse by using Gauss-Jordan elimination. In case, if we apply those operation, those procedure, but A cannot be reduced to the identity. We say that, we know that A, the matrix A is singular or the non-invertible. Now we continue with some other example that is just a little more complicated. A is a bigger one, 3 by 3 matrix. We need to find the A inverse. We apply the same things, A. Okay. We write the identity on the right hand side of A. We get that one. Now we apply elementary row operation step by step to transform A into the identity. So we get that thing. That is the first step. Second step is here. Third step is here. Fourth step is here. Fifth step is here. Up to this point is we are almost go to the reduced row echelon form, and finally it's here. Now the first part becomes already the identity. Then here must be the inverse of A. That we get already identity and A inverse is here. So the matrix A in that case is invertible and its inverse is that one. And you can verify it here. That is what we can see from the operation, from the Gauss-Jordan elimination. We can use that to find the inverse, and you can do it in your exercise. Now we continue to define the power of a square matrix. Here, suppose that A is a square matrix. We define A to the power 0 is identity, a matrix of the same sign. The second, if K is any positive integer, K is more than 0, then we define A to the power K equals the product A, K times. And it is very easy to verify that if we take A to the power A multiplied to A to the power S, you will get A to the power A plus S. Here A and S are integer. And more than that, if we take A to the power A and all together you take to the power S, it is A to the power A S, A time of S. All of those things is quite similar to the power of a number we know from the high school before going to USCH. In case D to be a diagonal matrix, you see you have D to the power K will be against the diagonal. And more than that, the entry lying on the diagonal will be taken to the power K. D1 now becomes D1 to the power K, D2 becomes D2 to the power K, and so on. And here are some properties of inverse matrices. If A is an invertible matrix and K is any positive integer, C is any scalar, but I require C is a non-zero, then we have the following property. The first property saying A inverse is again an invertible matrix, and inverse of that is A again. That you can see from the definition of invertible. It means B is inverse of B, then B is inverse of A or something. And if A is invertible, then A to the power K again is an invertible matrix. And in that case, the inverse of A to the power K will be the product K times of A inverse. It means A inverse multiplied by A inverse multiplied by A inverse k times, and we write it by this one. Again, CA. If A is an invertible matrix and C is a non-zero number, then the product CA is again invertible. And now, inverse of CA will be 1 over C multiplied by A inverse. With that formula, you see why we need C to be non-zero constant. Property number 4, saying that if A is an invertible, then A transpose is invertible, and inverse of transpose is transpose of the inverse. If you like, you can take it like your homework, but it's very easy to verify. Just only write down, and I leave it for you to see. But however, it is very, very interesting things because it will help you to remind what is matrix multiplication. Now, property number 5. If A and B, both of them are invertible matrices of the same sign n, then the product AB is again invertible, and the inverse of AB equal B inverse multiplied by A inverse. That is quite similar to the property for transpose. Property number 6, saying about the cancellation. In case C is invertible matrix, then we have AC equal BC. If AC equal BC, then we can imply that A equal B. That has named right cancellation property. And if CA equals CB, now we multiply, we have a product with C from the left, then we can imply A equal B if C is invertible. In that case, we say it is a left cancellation property. Property number 7, very important thing with the name. The name is Cramer rule. If A is invertible matrix, then the system of linear equation AX equal B has only unique solution, and that solution is given by that formula. And in next few weeks, you will study that when we continue on the determinant, and we know how to find the solution here. And we have property number 7 prime. Suppose that A is an n by n matrix, then we have the following statement which are equivalent to each other. The first one saying that A is invertible. The second saying that AX equal B has unique solution for any right-hand side in any column matrix B, or it is equivalent to the fact that AX equals 0 has only trivial solution. It does not have any other solution. So that is a finish of the lecture about the matrix operation. And because I tell you one of very important things, that is grammar rules, and it relating to the notion of determinant. So we continue right now about the determinant. That is lecture number 3. I will begin it right now. Lecture number 3 will deals with the determinant. Whenever we say about the determinant, we always says about square matrix. So in this lecture, we always assume that a matrix is a square matrix, except when I specify that is some size. So even the notion of a determinant is new one, but however, it's a very small number. You know it already from high school. You have computed in some exercise of you. I don't know, but even when I was a young boy in high school, I do it already. Here we begin with the first one. The determinant of a 2 by 2 matrix is following. Suppose that A is a 2 by 2 matrix with entry like that. Then the determinant of A denoted by that or that will be denoted by, you take product A11, A22 minus A21, A12. You multiply two things on the main diagonal and minus the subtract the product of entry lying on the other diagonal. Very easy. And the notation is here. You can put it here. Two vertical parallel line outside of the matrix, or you can just simply write it here. And here is an example. Very easy. I will not explain to you, and you can do it in your mind without writing it down on the paper. What I need to tell you that is determinant of a matrix can be positive in the first example, 0 in the second example, and negative in the third example. It can be any number. So now I go to the define determinant of any square matrix A. So first of all, I need to claim that for a square matrix, the determinant of that is a number. So whenever somebody asks you, please try to determine the determinant of to compute the determinant of any square matrix, you need to know it must be a number. It cannot be anything else. Now that number will be defined inductively. Inductively means quinine. We define it by quinine, means dần dần, step by step. The first step we define already, that is for 2 by 2 matrix, we define already in the previous slide. Now suppose that we define a determinant for any matrix of sign n-1 by n-1. And now if you are given a n by n matrix A like that, how we can define it? We can define it in next few slides, not right now. We have to do it as follows. First, we choose an entry Aij. And then we delete the entire i's row. And we delete entirely the j's columns. We delete that. So the rest will be a matrix of sign n-1 by n-1. And here we assume that, we suppose that we define already the determinant of any matrix of sign n-1 and n-1. So it means that if we delete those things, those rows and columns, and the rest, we know already the determinant. It is here. We know already here, after we delete the i's row and j's column, the left that one. And that one is n-1 by n-1 matrix. And because of that, we know already We know already the determinant, and that determinant will be denoted by Mij, and it has named the minor of the entry Aij. That is the first name. But more than the minor Mij, we define the cofactor of Aij. The cofactor is very easy. Just we take the minor Mij and we multiply by -1 to the power I plus j. And here is the example. Example, if we have A to be like that, then M21 to be that. M21 means we take that entry. We delete that column, delete that row, delete that column. They left only that one, that one, that one. And it is here. And then C2A means we multiply to the -1 to the power 2 plus 1. We get that thing. Similarly, we get that things and C22 to be that one. And so on. And here that slide is not so important. Just only to send you, to say to you that usually if you take a look at the formula for the cofactor, there is a factor that is a -1 to the power I plus j. Because of that, if you look back at the matrix, you will see the sign for the cofactor will be changed from plus to minus to plus to minus, and it is described here in the picture. Here you can see that is not very important thing. Now I want to tell you an example because that will be used in the next few slides, few examples. Suppose that we are given A with an explicit number like that, then if we are required to on the minus of A, we get it here. And if we are required to find on the cofactor of A, it is here. The cofactor is given by that, and the reason is here. Now we have enough things to define the determinant. I repeat that. We suppose that we define already the determinant for n-1 by n-1 matrix. Then, because of that, we can define the minor Mij, and then we can define the cofactor Cij. So now, if A is a square matrix of order n, the determinant of A can be given by one of the following formula. The first one is here. The determinant of A equals the sum of Aij multiplied by Cij. In that formula, I is a fixed, j runs from 1 to n. If you look at the formula here, I is a fixed and j going from 1 to n. And because of that, the formula has named cofactor expansion along the ith row. And in that case, I can be any number from 1 to n. I can be 1, can be 2, can be 3, up to n. That is the first formula. The second formula is following. Determinant of A can be the sum when I run from 1 to n. Aij multiplied by Cij, like that. Again, here j, the index j is a fixed, the index I run from 1 to n. Because of that, the formula has named cofactor expansion along the j's column. And again, we can do it for any column, the first column, second column, third column, and so on. Any. And here is examples. Determinant of a matrix of order 3. If we write down on the formula in the previous slide, we have 6 possibilities like that. We can expand the determinant by the first row, second row, third row, or first column, second column, third column, like that. And the first one has name expansion along the first row, and then here is an expansion along the second and the third row, and so on for the column. Okay. But however, in order to compute the determinant, in general, they did not require you to apply on the expansion like that. You can choose only one of that. And from the definition, we observe that the determinant of A equal determinant of A transpose, because we can expand any rows or any column. It gives the same reason. Here, I give you an example, a determinant of a matrix of order 3. The matrix is exactly the matrix in the example number 2. Why we use that? Because in the example number 2, we compute already on the cofactor. On the cofactor, we know already is here. I list it here. So we can apply six formula. It gives the same reason like here, 14. And as I told you, we need only to choose one of formula to compute the determinant of A, not on here. That is something like that. If you are required to compute determinant of A, you can choose anyone. Here is we expand it along the first rows, and you get that one. We need not to do that for on rows, on columns, only one. And now I explain to you by some example here. Because we can expand a dependent along any rows or any column. So the smart way, that is, it's up to us to choose which rows or which column to expand the determinant. So the smart way, that is, we should choose the rows or column which contain as many zero as possible. And here, in examples here, suppose that A is a 4 by 4 matrix like that. We need to find its determinant. And obviously, we choose this one. That columns contain only one non-zero entry. Then if we expand the determinant of A along that column, the formula will be something like that. But in that summation, that and that are on zero. So they left only that one. That is here. And is equal to that one. And for the determinant of 3 by 3 matrix, it is very easy for you. You can expand it along that thing. And then you get that. Then you can get that. Here is, we expand it along the second row, not along the first column, the second row, and the reason is 39. The next slide will show you a very practical way to find determinant of any matrix of order 3. You can find it even in the Vietnamese textbook. So I show it here for you. Suppose that A is any 3 by 3 matrix like that, and you are required to find determinant of A. You should do as follows. First, you write the first, second, and third columns of A. And then on the right-hand side of that, once again, you write the first column and the second column. So altogether, we have 5 columns like that. Now, next, you write the first, second, and third columns of A. And then on the right-hand side of that, once again, you write the first column and the second column. So altogether, we have 5 columns like that. Now, next, you write the first, second, and third columns of A. And then on the right-hand side of that, once again, you write the first column and the second column. So altogether, we have 5 columns like that. Now, you multiply the entry lying on the blue arrow like that, and then the reason you write it down here, and we add them together. We add on 3 product here. That is the first step. The second step, we do the second way. You multiply the entry lying on the blue arrow like that, and we write the product here, and then now we subtract these 3 products, and the reason will be the determinant here. The determinant of A will be here. We add the 3 product here, and we subtract 3 product here, and we get that things. That is a very practical and very easy to remember way to find determinant of a matrix of order 3. Example is here. A to be that, and we write again the first column, second column. Now we apply that. -4, 0, 6, and the other way, 0, 16, and -12. Then determinant will be, we add them together, and then we minus the reason here, and the reason is 2. So that is a practical way to compute the determinant of 3 by 3 matrix. I don't know if we can find the practical way to compute the determinant for 4 by 4 matrix. I don't know. Please, if you can find, you can show your friends. Next, I will show you the special case of matrix, which is very, very easy to compute determinant. That is a case of triangular matrix, and even the name is very easy for you to imagine. The first one has name upper triangular matrix. That is a square matrix, of course, and it requires that on the entry lying below the main diagonal are 0. Anything lower than main diagonal are 0. And because of that, it is a triangular, and then it is upper, because only the upper can be non-zero. And opposite to that, we have the notion of lower triangular matrix, means that is a square matrix which on the entry above the main diagonal are 0. Above the main diagonal are 0. Only those under the main diagonal might be non-zero. And it is easy to see that. Now the diagonal matrix, that is a square matrix, which is upper triangular matrix and the lower triangular matrix at the same time. We defined already before that diagonal matrix, that is something, a square matrix, which is on the entry outside of the main diagonal must be 0. And here we can apply it with the upper triangular matrix and lower triangular matrix. We get the same thing. It is a triangular matrix, upper and lower triangular matrix at the same time. And here, the observation saying a matrix is both upper and lower triangular is diagonal. And here is an example for you. The first one is upper triangular, obviously, because the shape is here. And the second one is lower triangular, is here. Any entry above main diagonal are 0. And the last one is a diagonal, because on the entry above and below the main diagonal are diagonal. n. For those triangular matrices, it's very easy to compute determinant. It is claimed as follows. Suppose that A is an n by n triangular matrix. It can be upper, lower triangular, or even it can be a diagonal. Then its determinant will be the product of the entry on the main diagonal. That is, in that case, we don't care about the other entry. We know immediately that the determinant of A will be A11 multiplied by A22 multiplied by A33 up to multiply to A and n. So very easy to find that. We don't care about other entry except those lying on the main diagonal. So that is the end of the class today, and the next week we will continue to study the way to compute determinant of any square matrix. We do it by the following way. We will try to transform it into triangular matrix. And how we can do it? We can do it by using elementary row operation. And that is what we are going to study next Wednesday. And before finishing, I tell you something. We have Miss Huyền, Phong Huyền, to be our teaching assistant. She up on the chat box some examples, some exercise sheet for you. It is your duty to do it, to do the exercise, and you submit it to her, and she will evaluate it. And we not only she, but on the lecture of this course, me and our tutor and tutor teacher in your tutor session, we evaluate on those things to give you the final evaluation by the end of the course. So please do on the exercise in that thing. So we stop here. Do you have any question?
Professor,
Yes.
Can you talk a bit about the minor and the cofactor of the entry? I still don't really understand those.
Which one?
The minor and the cofactor.
The minor. Okay. I will show you right now. It seems that I go just a little fast. Yeah. We need to define determinant of a matrix of size n by n. So first of all, we delete that. After deleting those things, they left that. But however, you should remember that we can get that because we choose an entry Aij at this position. And that one is already n minus 1 by n minus 1. So we know its determinant. And its determinant will be denoted by Mij, and we call it the minor of the entry Aij. You see, there is no Aij here. We delete already together with i's rows and j's column. It is not here. Because of that, here we call it the minor of the entry Aij. And the cofactor is the same thing like that, just only we multiply by that one. means it can be plus mij or minus mij. It depends on the position ij. Is it clear for you?
Yes, thank you.
Some more question, please.
Teacher, next time can you please slow down a little bit?
Okay. I agree to you because today is just a little long class because last week we shortened our class by some technical reason. So I am sorry for that. And next week I promise that I will slow down my speed.
Okay, thank you.
Okay, so see you next Wednesday.
Okay, see you again. Bye.
Okay,
teacher.
bye.
Bye, teacher.
Goodbye, teacher.
Have a
Thank you,
nice
sir.
weekend.
Goodbye,
Goodbye,
Professor.
teacher.
Have a nice
Goodbye,
weekend.
teacher.
Professor.
Goodbye.